So hello everyone and welcome to the MIT Biotech Group Entrepreneurship Initiative's first Fireside Chat of the year. Thanks to all attendees for joining and our speaker, Dr. Rob Carlson, for taking time out of his busy schedule to speak with us. While I said all participants try to stay on mute, we're going to have a Slido open for questions with a link in the chat managed by Elliot, but also feel free to drop your questions directly into the Slack, the channel. Depending on numbers, we may be able to call you at the end. And with that, it's my pleasure to welcome Dr. Rob Carlson to MIT. Over the last 20 plus years, Dr. Carlson has served as an investor, author, consultant, and more broadly futurist in considering biology as a human technology. Currently, Rob serves as the managing director at Bioeconomy Capital, which is invested in companies such as Zymergen, Synthase, Lumen Biosciences, and Arzeta. He's also principal at Biodesic, a strategy, engineering, and security consulting firm that works with numerous governments and businesses around the world on issues including pandemic preparedness. Rob has developed a number of metrics for measuring progress in biotechnology, including the so-called Carlson curves, which track the exponentially decreasing cost of DNA synthesis and sequencing. In addition to these roles, Dr. Carlson holds a PhD from Princeton in physics, is now an affiliate professor at the University of Washington Allen School of Computer Science and Engineering. And Rob, I know I've surely left out a number of different milestones and accolades, but I wanted to give you the opportunity to kick this off and introduce yourself specifically, maybe talking about your journey to go from a PhD in physics to the role and work you do now.
Thank you, Sam. Hello, everyone. Delighted to be here and chat with you. Delighted to be, well, I guess wherever I am, here at home. And thanks for showing up to chat. Yeah, so often the beginning of these conversations starts with, how did you get where you are? Or how can I get where you are as a student? And honestly, I have no idea. I just followed my nose the whole way and learned what I needed to learn. And I'm fairly thankful that the choices I made early on to learn how to learn and acquire the quantitative tools to ask hard questions and come up with answers have served me so well. And so to the extent that you guys are, pursuing those same kinds of skills at MIT, I just can only encourage you to learn them as thoroughly as you can and keep them with you as long as you can. I know I'm certainly rusty in some areas now, but nevertheless, it's that early skill base in being quantitative and asking those hard questions and trying to come up with answers that is basically what I do today, even as an investor or analyst or consultant to the US government or the UN or the WHO, whatever it is. I'm always focused on those quantitative questions and quantitative answers. And that distinguishes my approach from what many others do, in that I find in those halls of power or as an investor or whatever it is, that many of the other people that surround me are telling stories or offering opinions and not focused on quantitative questions and answers. I think that makes a big difference in the world when you can ask hard questions and ground the answer in reality as opposed to in what you or someone else thinks is true. So, I've always loved biology, but I didn't really like doing biology the way I saw it in biology classes. I didn't have a strong sense of what I wanted to be doing later, other than I wanted to do biology differently. So when I got to Princeton, sort of the odd duck in my class. There are only a couple of other people who were interested in biology, one of which, a name you'll recognize, is Michael Elowitz. He went to work with Stan Leibler and has done really remarkable stuff over the years. And I hoovered up whatever knowledge I could. I did single cell recording in fly brains for a while, and I realized that probably wasn't the way I wanted to spend my time for my PhD. And then I worked on single cells in microfluidics devices, my blood cells. So I literally bled for my dissertation. And there's another set of tools that have served me well over the years. Building gizmos as quickly and cheaply as possible has been a thread of my work in the lab over the years. And then eventually, as I was getting ready to finish, I was on a train from Princeton to New York to go to the med school library, because in those days we still had paper and no internet. And this old guy got on the train in Princeton, and I didn't know who he was. We started chatting, and he asked me what I was up to, and I told him. back and forth for a while, and we get to New York, and he says, "You should come work for me." And I was like, "Okay, guy on train, you know, whatever," because I was already in my New York frame of mind. Take everything with a grain of salt. And I get back to campus later that day and discover that Sidney Brenner is an important real guy, right? He wasn't in any of my textbooks, my physics textbooks. And I learned biology in a very kind of scattershot way. And so I hadn't connected at that time the name and his history with what was happening in molecular biology. And of course, he wound up inventing about half of what we know about molecular biology one way or another. Could have won 3 or 4 Nobel Prizes, finally just won one. But in any event, you know, I took that job, which was a good move. He was just starting a thing in Berkeley called the Molecular Sciences Institute. And I had 5 years to do whatever I wanted, which was amazing. It took me a while to recognize that Sydney, and there are lots of grand old men and women of science who are like this, but it took me a while to figure it out, that he would sort of go from one lab to the next that he'd started around the world sprinkling ideas about. And basically he would show up once every 6 months and confuse the hell out of me. And it took me a while to figure out that not everything he said made sense even. I couldn't make sense of it, but it just didn't actually always make as much sense as maybe would have been nice. But that's because he just had lots of ideas and he was able to, you know, spread them around the world to eager young minds. So eventually I just wound up going my own way. Again, I had the tools to ask these quantitative questions, and I got curious more about the future of biology as a field and as an industry, and started wondering if I could quantify in some way the current pace of biotechnology, and then the future, make some estimates about the future pace of biotechnology. And I did that and wrote those up. And that really was the kind of branch point for my life. And I was able to do that because I had a little bit of time and space to think when I wasn't being pressured by anyone to do anything in particular, except, you know, Sydney expected me to do something, but I could never figure out what that thing was. So I went and figured out my own thing. And then I bumped around in and out of academia for a while, between startups and academia a couple of times. Never really that happy with the idea of becoming a professor. You know, I had my application packet ready to go a couple of times, been asked lots of different times to become a professor or apply to become a professor in various places. And it never felt quite right. And one of the reasons was the academic grant cycle never appealed to me. And I've never been very successful at that. And that's because I'm usually looking further ahead than most people are. And I have a grant application, rejection rather, from the Unconventional Innovations Program at the National Cancer Institute that says, we can't give you any money to show that this is true because you haven't shown that this works. Which sort of defeats the purpose in my mind. You know, it was unconventional innovations and I was looking for money to go try a new thing, and they weren't interested in giving me any money to try something that hadn't already been shown to work. Well, you know, that confuses me to this day, and I find much of academic grant writing to still be that sort of stodgy. Anyway, so then I'm bouncing in and out of various academic jobs and in the garage, and I wind up eventually working on a molecular detection technology in the garage that spun out of what I worked on in Berkeley. It's a derivative of that. And I find that the technology works great. I can do everything I need to do in my garage to make this new technology go, but then I can't find any customers. So there's a, you know, early good lesson in life, entrepreneurial life, about making sure you have customers before you invest a lot of time in developing a product. And then that company, because, you know, we had expertise in the company and we knew some things, became a consulting firm. Eventually, which is Biodesic. Eventually, the consulting firm is spending a lot of time working with not just governments and big companies, but small companies, and that includes occasionally helping them raise money. And we were always too slow at that because effectively what we were doing was introducing the companies to our rich friends to become angel investors, and they take too long. And we missed some investments that would have been excellent, both for the company and for ourselves. So it made more sense to write checks. And someone I know here in Seattle was speaking to him one day, and I said, well, we're thinking about maybe trying to launch a venture capital firm to make this go smoother. And he said, no, 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 you should do that. That's great. I said, okay, thank you. I'll go home and I'll think about that. He said, no, 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 here's a check. You're running a VC firm. And I went, okay, I guess I'm running a VC firm. So years go by and we're pretty good at this, it turns out. We have 0 failures somehow after 6 years in operation. We thought we could do, much better than the industry average, which is 90% failure rate. We thought maybe we'd get to 50%, that would be awesome. And somehow we're at 0. Every time I say that out loud, I knock on all the wood I can find. And I think the reason, or one reason, is that we're very careful about the decisions we make in investing, and then we also work really hard to help our companies succeed. And it's true that a lot of VCs say that, but I think our track record is starting to speak for itself. And we're now beginning to reevaluate, are we really venture capitalists? Are we something else? We're operationally quite involved in some cases. In others, not so much. Basically, we do whatever we need to do. We wrote checks to Zymergen and then just tried to keep up. They ran so fast and never needed any help from us other than an occasional introduction or conversation. There are other companies where we do engineering, we do finance, we do operational stuff, whatever it takes to help. And that brings us to today. And in between, there's getting involved with the US government and the governments of Japan and UK and various bioethics conversations along the way. I served as an advisor to the Hastings Center for Bioethics in the early years of public conversation about synthetic biology. It led to testifying in front of the Presidential Commission on Bioethical Problems, or whatever it was called in that instance. Testified in front of Congress a couple of times now. I was at the White House last fall for the launch of the Bioeconomy Initiative. We can talk about all these things as the conversation goes on. But Sam, I'll turn it back to you, see if I missed anything or if you have a specific question.
Oh, that's fantastic. So I think I want to zoom in a little bit. You talked about quantitative principles really being your guiding principle. And I want to talk a little bit about those estimates you've made, particularly with respect to the bioeconomy. So maybe first you can talk, what is the bioeconomy as you understand it?
Well, there are different definitions. So the definition that what I'm really trying to get at is, what is the value of engineering biology in the US economy and in other economies? If you tune in to the Global Bioeconomy Summit, which is now virtual this year, of course, it's biannual. Went there a couple of years ago now in Berlin, with representatives from 800 representatives from 150 countries or something like that. The bioeconomy is biomass, and it's waste reutilization, and it's everything to do with biology. And I think that's important. And I would even expand that to include, invasive species and land degradation and the way we do or don't properly handle our waste streams, et cetera. This is all biology. We should be quantifying all of this, and we're terrible at doing all of those things, which means we don't understand them. And we don't know what's at risk. We don't know how much it would cost to replace them. All of these things need addressing better in the future than we have so far. And that's part of, in my view, building a circular economy or a sustainable economy or whatever you want to call that. We have to measure everything better in order to have any idea of what the hell is going on, and then also how to fix it. But for me, what I really want to focus on more is what's the value of synthetic biology or of biological engineering or of engineering biology or whatever label you want to slap on it. I want to know what's the quantitative economic return from the investments we make in manipulating DNA or otherwise manipulating biological systems. And so that question first came to me somewhat belatedly in 2007. I was on a consulting trip for a bank, traveling around Asia. I was in a different financial capital every day for 2 weeks. It's the sort of thing McKinsey puts you through. And for me, it was a different bank. It was CLSA, trading house. And I've been speaking about the future of biological manufacturing and biofuels and this and that. And I was taking a break in the hotel room, and there was this massive thunderstorm outside the hotel over the bay. And it was one of those times when it was, the metaphorical and real flash of lightning. It occurred to me, I didn't know how big it all was. I was talking about all these kind of more microscopic issues in some sense of how you get to a biofuel from a feedstock and how manufacturing might look and what subsidies mean and what other materials you can make. And it occurred to me, I didn't know how much money there was in the whole enterprise, which somehow I and my colleagues hadn't thought to ask to that point. So I figured I Google that, I'll find out. Someone must have answered that question. I'll use that in my next presentation later in the afternoon. There was nothing in 2007. And I don't know that I was the first person to ask that question, but no one had managed to put any numbers together at that point. And because the data was terrible even then, or especially then, it's not great today. But eventually, after many years of fumbling around, I get to the point where I'm pretty comfortable thinking about biotech as three different things. It's not just one thing. And those three different things are drugs, crops, and industrial products. And the reason I think it's useful to break it down that way is they have different costs. And they have different costs in part because there are very different regulatory regimes in those three different areas. And it leads to different product development cycles and time to market. So altogether, it's somewhere north of 2% of US GDP now, which makes it bigger than mining and some construction industries. I'd have to go look today about where exactly it ranks in other parts of the economy compared to other parts of the economy. But in the last downturn, the Great Recession, biotech continued to grow through the Great Recession, whereas most of the rest of the economy crashed. And if we hadn't had biotech, then the downturn would have been even more substantial. And if on average for most of the last 20 years, say, biotech is 2.5% something of GDP and somewhere in the neighborhood of 4 or 5% of GDP growth. So it's growing faster than the rest of the economy. Depending on how you look at those numbers, GDP growth from biotech during the Great Recession was 6, 7, 8, 10, maybe 10% of US GDP growth during those years. So the fact that there was this massive chunk of revenue in this area that nobody was looking at was astonishing to me. And we're still not looking at it very well. The reason that we don't understand it is because of a structural flaw in the way we measure things. And that is, if you don't know what a NAICS code is already, I'll introduce you. It's the North American Industrial Classification System. And in principle, everything in our economy has a NAICS code. Your shoes, your phone, the monitor in front of you, everything, your glasses, your clothes, everything has a NAICS code to describe how it was made, where it came from. That's where our labor statistics come from largely. What's the benefit of this industry or that industry, how many people are working, and all these things are tracked using NAICS codes. There are no NAICS codes for biotech. So we're just oblivious to this massive part of our economy that the US government doesn't measure. And so I've talked to 3 White Houses now about trying to fix this. And every time I bring it up, they say, oh, that's a great idea. We'll do that. And nothing. I keep at it, but nevertheless, we're not going to get better data on the bioeconomy until we fix that particular problem. I'll pause there and see where you want to go.
So it seems this, in your market breakdowns, you have the industrial component of the bioeconomy as a surprisingly large share. Mm-hmm. Can you speak a little bit about maybe why this is both a little bit less visible? It seems like, especially from where we're sitting in academia, there's a big emphasis on drug hunting and therapeutics. Mm-hmm. So can you speak a little bit about why it's less visible, and also how your thoughts on industrial biotechnology have evolved since early days in biofuels?
So to put some numbers on it, it's something like $150 billion in revenue in the US, where 100 billion, give or take, again, the error bars are pretty big here, are biochemicals. So all of this is published first in Nature Biotech a couple of years ago with a model, the data set, and then a numerical model to try to figure out where what the trends are and where it's going. And then second, we keep this updated every couple of years on bioeconomy.capital on the bioeconomy dashboard. So you can go have a look at the charts and look at the methods and the models on GitHub if you want. So you can dig into it. We only update it every once in a while because it's still really hard to come up with the data for all this stuff. So that said, the industrial data largely comes from Agilent. It's consistent with other kind of pot shots at estimating this over the years. Agilent has paid a couple of times for internal marketing surveys that appear to do a pretty good job of quantifying how much money there is and how it's broken down across different subcategories, whether that's pharmaceutical ingredients or agricultural inputs or things that are displacing petrochemicals from the market or fuels. And so way back when, 2010 or so, 2007, really when I first started doing it, but then 2010, I think is when I first published my numbers, they were wrong. And they were an underestimate because I didn't have access to the Agilent numbers and there were still, a guess here and a guess there. But so why are they wrong? Why is it so hard to figure out what the hell is going on? And the answer is, it seems like many of the things that we imagine are made via chemical processes, via petrochemistry, are actually biological processes. The fact that we don't know, I think, is pretty interesting. And I've written some blog posts about this. There's one on the Bioeconomy Capital website called "Seeing the End of Oil," where I work through how we're going to displace 100% of a barrel of oil eventually. Biology is only going to be responsible for a small fraction of that. But it's interesting that a compound is a compound. You can't tell in principle unless you're really thorough whether some carbon compound came from petrochemistry or came from biology. It behaves the same. Maybe you can do some isotopic analysis or something and figure out that they came from different sources. But the fact that we can make everything that we now get from a barrel of oil using biology means that now we can just drop all those things into our economy and they're invisible as far as the use goes. And I think that's the future, right? Every time I go look at an economic analysis, it's clear that biology can make anything we get now via petrochemistry better, faster, cheaper. It's now a matter of finance. Can you find someone to pay for that substitution? And that's a more difficult problem because if you as a biotech entrepreneur go to a banker and say in a couple of, or any kind of financier and say in a couple of years, I'll be able to outcompete this high volume petrochemical or high value petrochemical rather by 20% in terms of cost, that's great. And you will eventually win, except the banker to first order is going to say, but tomorrow I can go invest in real estate at 20% and be making 20% while you're trying to get your process scaled up and out the door. So I'm going to go do that instead. And that says until the incentives for finance change, we're going to see slow rollout of biological manufacturing. And that means for us as investors, our thesis has changed over the years. Initially, we were planning to directly target low volume, high value petrochemicals in our companies to land and be able to make money with smaller volumes, land in the marketplace. And now it makes more sense, I think, to target things that you just can't get to from petrochemistry. So that's what Zymergen is doing, for example, with hyaline. You can't make hyaline plausibly using petrochemistry. You can only make it using biology. Our Zeta similarly can make a wide variety of compounds using engineered enzymes and enzymatic pathways that you cannot make using petrochemistry, or cannot plausibly make using petrochemistry anyway. But they're relatively straightforward to get to using synthetic biology, enzymatic engineering. And that's the future.
So along the same lines, you've talked, and some of your writing talked about the future being somewhat distributed because the cost of vat and yeast is much lower than building like an oil rig or whatever facilities you need. But it also seems like we're entering this regime where there's a few larger companies of scale that have the financing expertise to do these engineering projects. What enabling technologies do you see, and how do you see us overcoming this kind of development of a few key monoliths?
So I think it's important to distinguish where we are today and what the lift is in terms of investing in making any chemical or displacing a petrochemical from the market, from where we're going to be 20 years from now or 30 years from now. And to put some numbers down. So the marginal cost of doing anything new with petrochemistry is something like $10 billion, could be $20 billion. What that means is that's how much it costs to build a new petrochemical processing plant or refinery or distribution plant or something. It's not cheap, right? If you calculate the per liter cost of these facilities, it's quite high, as is the energetic cost of processing the raw material into any of these products. And if you compare the per liter cost or per kilogram cost of doing something by brewing or with a cow, if we knew how to make a cow that could make these compounds, which we don't yet, but we will soon, then it's quite clear that 20 or 30 years from now, people will have stopped investing in the super expensive petrochemistry and instead will be investing in the much less expensive biochemistry. How we get from here to there is another matter. So at the moment, we still have all these incentives in place for building out petroleum refining and petroleum processing. Having said, so, even a month ago, if you'd asked me that question, I might have a different answer than today. If you go read the Financial Times or Bloomberg, just in the last few weeks, it seems that every day there's a story about petroleum companies turning away from petroleum and embracing renewable energy, wind, solar. They're trying to get out of carbon, liquid carbon, coming out of the ground as a business model. And because they can see finally that that's coming too. And one of the leading indicators there is that if you look at the cost of capital for investing in a new renewable energy project versus a new petroleum or fossil fuel project, it's completely changed in the last year. So it used to be that risk capital found a home with renewable energy, but now it's fossil fuels that are the expensive, risky projects. And again, that's a leading indicator of how investment is shifting, but it's not going to be fast, right? We're talking about gigantic volumes of material that move through the petroleum industry at the moment. Only 2% of the atoms that move through the petroleum industry wind up as petrochemicals. So there's a breakdown in that Seeing the End of Oil piece, if you want to dig into that. And that gives me hope, right? So we only actually have to replace 2% of the atoms, or displace 2% of the atoms that move through the petroleum industry to be able to fully replace the entire petrochemical industry with biochemicals. How do we do that? Well, so we need better ability to develop processes and move processes around. There's a concept called design for manufacturing, which is how we get our cars and our airplanes and our phones, where you can start at a whiteboard or on your laptop and design whatever you want to make using CAD tools. And those CAD tools know about the manufacturing process. And that enables you to then transfer your design through various build, test, scale up parts of the manufacturing tool chain until you can manufacture at scale. And of course, there's bumps in the road, and you still have to do testing, and people make mistakes, machines make mistakes. That's true. But that infrastructure exists, that tool chain exists to manufacture all kinds of objects. But we don't have it for biology. So we don't have the ability to start at a whiteboard, design a process, or point to a particular molecule that you want to make with an artificial enzyme or synthetic enzyme network, something like that. And then instantiate that easily into an organism, and then instantiate that or put that organism into a manufacturing process, and then downstream processing, et cetera, all that stuff still has to be worked out. And we have invested in some of that through Arzeda and Synthase and Riffin and Zymergen, for example. But there's still so much more that has to get built. So, how do you go from your 1 liter benchtop reactor to a 1,000 liter sort of mid-scale reactor and get the same results? How do you then move from your 1,000-liter bioreactor to however big a bioreactor you need for your manufacturing process and still get the same results? These are problems that are not solved yet. Technology doesn't exist yet, although maybe you can see it, emerging here and there. And we need more of that. We need a lot more of that. And then somewhere down the road, we also then have to handle scaled manufacturing, distributed and scaled manufacturing. So many years ago, I started wondering what would happen if we needed to repurpose brewing to make vaccines, or repurpose brewing to make, some countermeasure. And this was in the wake of SARS 1.0 and H5N1. So I've been thinking about that for a long time, but I'm not seeing all the pieces come together, right? So today we're struggling still, we're faster than we were even a couple of years ago to go from identifying a threat or identifying a thing, anything we have to make, and moving it into early stage testing. But it's still hard to make enough of anything to have an impact on the world in a hurry. Here's an example of a thing that we invested in and that's working out very well. It doesn't solve all these problems, but it solves many of these problems. So Lumen Biosciences is the only organization around that knows how to stably engineer spirulina, which is an algae. It's been a food for millennia. You can go to any health food store and buy spirulina. If you drink a green drink, odwalla or whatever, it's got spirulina or kale or spinach in it, or all three. That's what makes it green. And so we invested in Lumen because they had the ability to stably engineer this organism, and second, had a vision of biomanufacturing indoors in bioreactors to handle variations in yield and variations in weather, et cetera, that could make them an interesting business. And we thought, great, this is an orthogonal manufacturing play to anything else that exists. It's photosynthetic manufacturing, basically, indoors. I'm a veteran of having looked at many algal biofuels plays over the years, and none of them made any sense. And I really wanted to stay away from something like that. And in fact, when I was introduced to Lumen, I thought it was nuts. I agreed to have a beer with them, and I would, share with them why I didn't think it was going to work. And then 3 hours and 3 pints later, we were still at it because they really did have something good. And we invested in them as a pigments manufacturing as a first step, right? So they can make pigments in food quality pigments and flavorings in spirulina, because they can do the engineering that are much higher quality than you get from the natural bug. Time goes on, the Chinese enter this market, and maybe even though we can compete in it, it's not such a great market to go after anymore. But then a chance conversation with the Gates Foundation leads Lumen to try making antibodies in spirulina. And it turns out it works spectacularly well. And so now we have this opportunity to have these bioreactors indoors plugged into the grid that turn electricity into drugs, which is mind-boggling to me, not because I didn't see it happening. I did see it. I thought that was going to happen. That's been part of our plan the whole time. It's been on our roadmap at Bioeconomy Capital from the beginning, but I didn't think it was going to happen so soon, but it's happening now. So, they are in effect turning, well, not in effect, they're going to be turning defunct industrial facilities throughout Washington state into drug manufacturing plants, because there's a power substation next to a building. It's no longer an aluminum smelter. That doesn't work in the US anymore, or at least not in Washington state, even with rock bottom electricity prices. But we can take advantage of that, right? So we're going to plug algae growing boxes into the grid and make drugs, which again is not where I thought that was going to go, but I'm perfectly delighted that it's going that way. And it demonstrates the idea that you can do distributed biological manufacturing once you get control of the organism, once you get control of the environment that the bug grows in, and have a way to scale it up, which they do.
That's fantastic. And I think that really gets to the question of how, a smaller company can compete with one of these larger, Zymergen Ginkgos in an interesting way. And
well, I should also, before you go on, I should say, as much as I love Zymergen, we're seed and A round investors in Zymergen. So, hooray, rah, rah, go, go, go. they are still operating, they're still demonstrating hypotheses, right? They had ideas about how they could change the world. And yes, they are shipping product, and they have helped other companies improve their products, but that doesn't necessarily make them a gigantic success yet. There's a difference between the scale of finance that people buy into and the scale of operations that startups work at. And I'm not sure there's anybody across the synthetic biology space that's truly demonstrated the scale of operations yet. There's still a lot of storytelling about what can become true. I fully believe it will become true, but I just think it's important, again, quantitative questions and quantitative answers, to be very careful about what the scale of a company might be just because it's attributed to be a certain size based on its valuation, as opposed to the kilograms of product it ships in a year.
Makes sense. That's a really nice distinction. I think maybe the last topic I want to touch on before opening this up to some questions we have from the audience is biosecurity. And I think with COVID, this is very much on a lot of people's minds, preparing for potentially engineered threats in the future. Can you speak a little bit about how your experiences with DIY bio, garage bio in the early days have influenced your current thoughts on biosecurity, and where your head's at with all these issues?
So I've written a lot about biosecurity and garage biology, the intersection, and the economics of that over the years, and I brought that to the table early on when I was thinking about the future of DNA synthesis and who was going to have access and what it would mean when the price fell and access increased. So back in 2003, I wrote a paper that laid out the first exponentials, the little data that was available, but nevertheless, it was enough to at least make sense that there were exponentials in play, and then also asked what would happen if we attempted to constrain access to these technologies. And even at that point, I was asking what technologies are more like biology and less like biology, and what can we learn from the history of regulation and security in those areas. And I recall in 2003, after that paper was published, I was summoned to give a talk to a National Academy panel in DC that was examining these things they wrote something that became known as the Fink Report, which was the first stab at developing guidance for the federal government about how to deal with potential threats. This was in the wake of the anthrax attacks in 2001, and was before the H5N1 and SARS, or I guess it came out just about when SARS was happening, SARS 1.0. So I show up to this room and I'm expecting it to be full of scientists and people from the academy, but also along the back wall, there are a whole bunch of people in suits, again, literally and figuratively in the shadows in the back. And I thought that was odd. They were the only ones in suits. And so it turns out, as the talk goes on, that these are spooks. These are people in the security community who have been charged with trying to understand these problems as well. And even then, what many of them did was turn to their experience with nuclear security, guns, gates, and guards. And that kind of approach does work with nuclear security, because fissile material is hard and expensive to come by, at least purified fissile material. And then bomb making is still hard and expensive, even though it's less hard and less expensive than it used to be. You still have to have the fissile material. So if you can put a fence around the fissile material and stick some guards in front of it and put some locks on the doors, then that goes a long way towards implementing security. But biology is what you see out the window, right? And if you know what you're doing, you can reconstitute the biological toolkit from purifying pieces from nature. And now we also have the ability to reconstitute the molecular biology toolkit from synthesizing genes from scratch and building out that infrastructure as well in any lab anywhere. So I'm a participant in this project that Microsoft has funded to do DNA data storage at the University of Washington. And one of the postdocs built a soup to nuts DNA data storage system, write, store, read, where the write part is single channel. It's not high throughput. It doesn't work fantastically, but it still works. And it's basically cobbled together with parts from the hardware store. And so the notion that you could somehow control DNA synthesis by implementing restrictions on access to hardware stores just doesn't make any sense to me, never made any sense to me. And for me, the model of security for biology to look to is the one that we already know from computer security, which is as much transparency and openness as possible, because it allows you to have more eyes on more bugs, literally in this case. And then there's the problem that every implementation of security that I've seen in areas that look like biology, whether this is methamphetamines production or printing even, if you go back to the 15th century, it's already clear that printing is a democratized technology. And when you try to control access to printing, all you do is create other printers elsewhere, as it were. The same thing is true for biotech. If you attempt to constrain access to biology, all you're doing is incentivizing people to go create that same production capacity elsewhere. And there's no physical way to prevent them from doing that, which means that if you implement restrictions, call this a hypothesis, if you like, attempting to be as hewing as close to the scientific method as possible, even in developing policy, what's the data to support your recommendation for policymakers? And in this case, all of the data that I'm able to find says if you attempt to constrain a democratized technology, it just leaks out through your fingers and shows up elsewhere. So you basically incentivize the thing you're trying to prevent through these security measures. Prohibition, of course, in the US is another fantastic example of that. Complete failure incentivized all kinds of behavior that the law and the constitutional amendment were intended to prevent, but again, were totally counterproductive. And so I would love, if there was data suggesting that we could come up with a policy that created security as a result of restricting access, that would be worth considering, right? We should put that on the table and see if that's the best way to create safety and security. But I can't find any examples of anything like that for any technology remotely like biology in terms of its cost of access or its distributed accessibility, its democratization. It just never works. So why would we think in the future it would work in this area when it's never worked anywhere else? And that would then, open, if you want to go down this road for future conversation, we can try to bring all that other experience to bear in Washington, D.C. on policymaking. And it's, it's a hard road to hoe. I keep working at it, but there we go.
And in practice, do you think we're, losing this battle? Is there a very real possibility that this will be restricted in a serious way?
Okay, so first, more data, an anecdote, because the, big error bars again. In the mid 2000s, about 2010, I can't remember exactly when this happened, the Department of Health and Human Services, which sits on top of the NIH, promulgated some restrictions on which DNA synthesis providers you could use if you receive federal money, otherwise known as the screening guidelines. And these are the result in part of a report that the Sloan Foundation paid for, came out of MIT and some other organizations a few years earlier that looked at options for governance of DNA synthesis. So there were some recommendations made, and then eventually screening was chosen as a way to try to improve security. And at the time I said, again, this historical based approach, this has never worked anywhere else, so why would it work here? What you're going to do is incentivize people to go set up DNA synthesis operations that are not subject to your security regulations, and in particular, do not do screening. And I was told I was full of it by lots of people. And then there was another Sloan-funded examination of what was going on in China a few years later, and it turned out that there were 3 tiers, as it was described in the eventual report, of DNA synthesis provider in China. One complied with the screening recommendations from the HHS, and those companies were attempting to market outside China and participate in the international biotechnology market. There was another tier of DNA providers that also complied with screening, and they mostly looked internally, but also aspired to be on international markets. There was a third tier of synthetic DNA provider that was described in at least one case as the mom and pop DNA shanty, where the providers, lived over the lab. And they explicitly served markets that were excluded from participation in the screening. So the screening guidelines came with an unofficial gray list of countries that shouldn't be served: Iran, Syria, places where you didn't want maybe interesting pieces of DNA or concerning pieces of DNA being shipped to. And as described by the people who went and looked in China, those providers of DNA synthesis existed specifically to serve the markets that were on the gray list. And so once again, that thing happened that, you predict would happen with a distributed democratized technology, and that is attempting to contain it, incentivize someone to go around. Always happens. Now, here in the United States, just as we speak, California is considering a bill that would require, the California legislature is considering a bill that would require all DNA synthesis providers in California, I don't know the exact wording, to implement DNA screening imputatively as a security measure. I think what this actually is an economic barrier to prevent other people from engaging in the market. But nevertheless, the top line thing it would do is require DNA synthesis providers to implement screening, and that's an expensive thing to do, without any thinking whatsoever about the consequences of attempting to constrain access to this technology. And inevitably, again, it's going to result in some kind of escape, some kind of proliferation, some kind of creation of more insecurity, precisely as a result of attempting to, make everything more safe. It's mind-boggling to me that we're still having these conversations, but we are.
And so we have about 10 minutes left, and the last thing I want to ask you about, and then look to Slido if we have time, is particularly about measuring progress going forward. Do you think that the cost of sequencing and synthesis is still the bottleneck, and it's still a good measure of progress? And if it's not, do you have any thoughts about how we should be measuring progress going forward?
That's a great question. Did I pick the right metrics? Are these the right metrics? And I don't know if
are they the right metrics going forward?
Yeah. I think the throughput of your device is still a useful thing to know about your device, right? And so if ultimately you want to know about if you want to screen samples in your lab, or if you want to do discovery out in the field, or if you want to have a test and measurement tool for any kind of process, then the throughput of that test and measurement gear is important. And so to the extent that productivity, for example, which is one of the metrics that I tried to come up with data for, is useful, historically, it will also be useful in the future, right? Knowing how your instrument works is an important thing, and having high throughput and low error bars is certainly important. Is price going to be so important going forward? And to the extent that people say price inhibits them from using sequencing, or price of synthetic DNA prohibits the use of more synthetic DNA, then yes, that's an important metric too. Is it a bottleneck though? And I'm not so sure that's true anymore. I thought for some time that the difficulty we have with synthetic DNA as a business model, providing synthetic genes, et cetera, is that we don't know how to effectively use all the DNA we already have access to in biotechnology as an industry. We keep coming up with new ways to make more libraries and do more screening. That's really different than forward design, and really different from the design for manufacturing approach. And it's, screening is not how we build airplanes that fly, or phones that work. We make those things function in the economy because we measure carefully, and then we construct carefully. And we wind up with systems that behave predictably. And so tools that facilitate that process, I think, and metrics of measurement of that process are going to be more important going forward.
Awesome. And I think Elliot's going to jump in with a question or two from the audience.
Yeah, so I'm going to ask some questions from the audience, and maybe I'll sneak in a few questions that are just my own, if you guys know the difference. So I want to ask about, so you talk about DNA synthesis as perhaps being almost an example of what you were talking about before, as something that's being developed, but it's not really clear that we really need it at the scale, the industrial scale that you're really interested in. So I'm curious if you have any thoughts on Kevin Ness's Inscripta company that has received hundreds of millions of dollars in funding to produce these machines that will, are in theory are benchtop synthesizers, which, seem to me like they could change the way that startups have access to the ability to produce genes, but perhaps are a little bit overhyped and overfunded is maybe my thinking, but I'm curious if you have thoughts.
So I'm not gonna discuss any particular DNA synthesis company, I think, but rather the industry as a whole. We can dig into that a bit. So for many years, startups came along and said, DNA is the new transistor. And look, there are exponentials in DNA, and just like there were exponentials in transistors, Moore's law, whichever version of that you like, DNA is going to change the world. And again, I wrote about this a long time ago, and it didn't have as much an impact on the storytelling as I'd hoped. But DNA is really different than transistors in the way that we use both of those things today. So if you go get a new phone, you want it to work better, faster, whatever, than your last phone. And the way that generally happens, it has more transistors in it. That is, the manufacturing capacity of transistors is directly correlated with the value of the thing that you paid money for, your phone, your laptop, whatever, your watch, whatever it is. With DNA, you need one copy of DNA to produce N copies, valuable copies of whatever thing you're making. So however much the DNA is actually costing you to get to whatever that one sequence costs you, and all the iterations and all the variety, all the design, all the screening, whatever, it doesn't matter because the revenues from the thing are decoupled from the cost of DNA. And so for years and years, companies were founded based on the idea that that distinction didn't exist. But the problem is every single DNA synthesis company has tripped over the fact that it does exist. There is no coupling between the value of the DNA, the number of different sequences you can make, and the final value of a product in the marketplace. Because it's not DNA, it's a barrel of chemicals or whatever it is, right? So that's problematic. Whether everybody needs a DNA printer on their benchtop or desktop, maybe yes. I can think of times in my life where I could have used that capability and yet I got by without it. So, how much commercialization effort goes into building that box and making sure that it works and marketing that box and making sure it has consumables, when again, the output of the thing is actually not the most valuable part of your development process. Like if you spent 1% of the cost of your product development on DNA, that'd be a hellaciously expensive DNA, right? That would be crazy. So nobody, in the end, it never works out to be even that high. So I just don't see that. There is, however, an impending use of DNA where the value of the final product is the volume, depends directly on the volume of DNA you can make, and that's DNA data storage. And when I started with Microsoft on this project, I thought it was a bit of a lark. I knew some things about the pace of change and how fast this technology was coming along, and I thought I'd maybe learn some more. And very rapidly, it became clear that this was the future, and it was going to happen, and it is happening. Is it happening tomorrow? Probably not tomorrow because we have some more work to do, but it better happen really soon. And the reason I say it that way is that the amount of data we're producing and storing is increasing hyper-exponentially, not just exponentially. And even though we know how to store that data on tape, for example, hyper-exponential amount of data needing to be stored means a hyper-exponential amount of tape, which means a hyper-exponential number of tape factories and a hyper-exponential number of tape storage facilities. And even if technically that's feasible, it's economically implausible. We have to switch to something that has completely different characteristics than anything else that we're using right now. And the only thing that I see that meets the quantitative metrics that I've come up with is DNA. And that means we're gonna probably have boxes that can write copious sequences, different sequences, distributed around. And the amount of DNA that will, the number of sequences anyway, that will make to store data will vastly exceed the amount that we use in the biotechnology industry, which means that a completely orthogonal demand on that DNA will cause technology change, is causing technology change and development that will then feed back on biotech at some point in the future when, I don't know. And, you know, are you going to use the same box that you use to write DNA for data storage to make your genes? I don't know. The technical requirements are different. Maybe, maybe not. We'll have to see how that goes.
Yeah, thank you. Super thoughtful answer.
So I think we're at 5. So I want to be respectful of Dr. Carlson's time.
I can stick around for a little bit if you like.
Do you want to do one more question?
Yeah, so let's get one of these questions from chat. So someone wants to know what your thoughts are on the cloud lab movement and if you've invested in any startups that use cloud labs.
Yeah, complicated question. I'll do it as quick as I can. So whenever I have been involved in a technology development project or just doing science, it's always been important to me to be able to, you know, get it into whatever I'm working on up to my elbows, take it apart, troubleshoot it. Things always go wrong. Recipes don't work, whatever it is. And so personally, I don't understand how a cloud lab helps me solve my problems when I keep having that kind of problem I have to solve. And then if you ask big customers like pharmaceutical companies whether they want to use cloud labs, they also have the problem. They don't want to see any IP transfer. They just don't want to let it out of their hands. You know, not that the cloud lab won't sign an NDA, but rather just the fact that you transmit bits from here to there means now you can't be sure the security of those bits. And that's also now true for atoms because we can sequence, and I mean, there's no way to guarantee the security of a cloud lab. And so I have questions about that. I think that the limited success of cloud labs so far is related to both those things. You know, there are specific design problems that some of the other now less successful cloud labs built for themselves. What we have invested in is the electronic infrastructure to try to facilitate process development and technology transfer within organizations. So Synthase and Riffin are both examples of that, where in analogy to what happened with chips, originally you had these stovepipe vertically integrated companies, with Zymergen or Ginkgo would be an example of that today, where they had to develop all their own tools internally. They talk to their automation. But then you couldn't actually use that automation if you didn't also, basically, if you weren't within the stovepipe. But then Moses came along and things changed in chips and everything became horizontally integrated or distributed even, because it's hard to maintain a tool and maintain the process that uses it and use it for, you know, design and everything. So that was a natural progression. This is true in other industries as well. And so what we see coming is tools that facilitate the ability to do design for manufacturing and biology, but that are used within a particular organization and that are used to transfer technology within that organization and then maybe to somebody who's acquiring a process or acquiring a company, something like that later. I don't get cloud labs. I'll leave it at that.
Okay, yeah, and let's do one more of these questions from the audience. So there's an infectious disease doctor in the audience who works on diagnostics for invasive fungal infections.
It's a small audience. Do you want to? Is this? I'm assuming Michelle.
Yeah. Do you want to just ask your question? This must be Michelle, right? Is that?
Yeah, it's me. Hi.
Yeah. Why don't you just ask the question?
Hello.
I forget exactly what I wrote, but I wrote that I'm also working on diagnostics for invasive fungal infections. And one of the reasons that it's so important is that clinically we're seeing a lot more new yeast species that are multi-drug resistant with like global warming and climate change. And it's certainly something to think about in terms of like food handling and also hearing about these bioreactors. The other reason it's so concerning is that we have very few antifungal classes. So with the rise of multi-drug resistance, you know, we're sort of scrambling. So I'm wondering what sort of like thoughts the energy industry has put toward the potential for these as bioterrorist agents or agents of bioterrorism, or what would happen if they became like sources of human infection.
Okay, that's interesting. I think, although I'm not sure, that most of the strains of fungi that are used in biomanufacturing are not human pathogens. I would have to double check that, unless somebody knows differently. I don't think there's tropism, but I could be wrong.
So that's true. Thinking about like yeast brewing for beer, Saccharomyces, typically not a human pathogen, but for our like sickest, you know, immunocompromised people, it has been reported as human infection. And certainly like mutations, they're not immune to mutations too that can make them multi-drug resistant pretty quickly.
I mean, there's an entire conversation here about biosafety, things getting out of labs that might be dangerous. There, I think, is less concern about industrial platform organisms becoming human pathogens. That said, you know, there are those cases that show up occasionally of auto-fermentation, right? People who have yeast infections that create fermentation inside their digestive tract, and they're constantly inebriated as a result. So it can happen. The other thing I would say, though, is that the increasing ability to respond more rapidly to outbreaks. We're living through an example when we don't have it figured out yet. We're imperfect, and yet it's much better than it was. I'll come back to Lumen briefly. You know, the fact that they can make antibodies, neutralizing antibodies to things in your gut or on your mucosal membranes for 1,000-fold less than any other manufacturing technology. And they can, you know, today it's 6 months to get a new strain. Penciling it out, it looks like they can get it down to 6 weeks, maybe even less than that. And then because the bug grows super fast, they can be making millions of doses in weeks. I have hope, you know, more hope than I've had in 15, 20 years, that we will be able to address problems like that. So, for example, Lumen has an approach to combat C. diff infections, multi-drug resistant C. diff infections, using an antibody cocktail that no one else can approach simply because of the cost, right? So they can do multiple antibodies developed to work in concert at the same time and get those into manufacturing in a matter of months, 6 months-ish, we'll see. Whereas if you were trying to make antibodies in a human cell line or even in a standard industrial platform, it would take you much longer and would be much more expensive. So that's not to say that Lumen will be 100% successful with what they're trying to do, but rather I see a lot of progress in using the tools of modern technology, modern biotechnology, including the scalable manufacturing, so that I think we're going to be okay. I want to be too confident, right? But I think it's going to be all right. We have a lot of work to do. We have to actually implement all these things.
Cross our finger for phages.
That'd be great. You know, I keep waiting for all the phage work that happened in the Eastern Bloc to come back to the West, and people say it's happening, and then it never shows up, and I don't know why is that true? Why it's preventing us from
I think it'll come
phages.
out of San Diego first. So.
Okay, great.
I'd love to ask a question about just the sort of regulation and government's approach to biotech and bio-industrial systems. So, one thing that I learned when I was learning about the sort of industrial engine of America was, how we had large control over manufacturing for many, many years. And one important thing that comes from control of manufacturing is control of manufacturing innovation, and how sort of like having control of the manufacturing sector just begets economic growth by means of that innovation control. So I'm wondering if bio-industrial applications represent sort of a new forefront for us to regain control in America of manufacturing and manufacturing innovation. And I wonder if the government's thinking about it in this way, and if we're people, I figured you would be in the know about this, if people are actually pushing for us to do this. And I really hope that they are. So I'm hoping that you answer my question with a yes.
Well, I have a paper that's about to come out from Johns Hopkins where I specifically make that argument about design tools for biological systems, where the historical analogy that we've just seen demonstrated is in the licensing controls for chip design and chip processing equipment, in terms of limiting access by Chinese companies, Huawei in particular, and Chinese fabs. So it was asserted maybe 9 months ago, 6 months ago, that it was going to be very hard for the US to regain control of silicon and have any impact on the Huawei's ability to roll out 5G, because they had what they needed to make chips for 5G and then make IT platforms built around those chips. And the first efforts by the Commerce Department to restrict Huawei's access didn't work so well. They were full of holes. Huawei figured out how to get chips and get access to tools. And then what the Commerce Department did was restrict the licenses for software for test and measurement and design of chips, as well as some particular tooling that you need to make small line width chips of certain complexity. And now it's being talked about as an existential threat to Huawei's existence, and similarly, other parts of the Chinese telecommunications industry. And so to the extent that, here we are in month 8 or maybe 10 of the attempt to regain control over that kind of technology, maybe the US government has sort of kind of figured it out and is making some progress at it, but only in that area, right? So again, here, historical example, rapidly developing in a related area. Can we do that again with biotech? I think the answer is yes. If I look at where the best design tools are, where the best design capability is, I think it's here and in Europe. And so if you wanted to build a moat around that, I think you could do that. I'm not saying that we should do that. That's the best course of action. But as far as successful implementation of policy, it's something that we can try, or at least we should be aware of.
Yeah, and I know Sam wants to end the chat. I'll just quickly ask, because I'm so greedy with my time with you. One thing that this predicts is a growth of companies whose sole purpose is to be sort of reactors for hire. So I think about like this, there's this Forge, I'm not asking you to comment on specific companies, this Forge company that's coming out of the Midwest that's meant to be an adenoviral vector, sort of reactor for hire. And I'm wondering if that industry is something that you see as promising.
I think the future of biomanufacturing is beer and cows. So beer, we understand. Beer is an economic model we understand. Beer is a manufacturing model we understand. Don't really yet know how to repurpose those organisms in that context yet, but I'm pretty sure that's coming. But there will be bioreactors for hire that look just like beer. Yes, I think that's coming. And for example, Synthase eventually, or if it's not Synthase, it'll be some other company, will get the APIs right so that you can walk up to a company like that with a process using an organism that brewer, for lack of a better word, understands. And also the API has the right settings in it so that you can operate on their equipment, which is not true for most biomanufacturing operations today, right? You show up with your process that your startup has figured out how to use today in your 1 liter bioreactor. If you show up to somebody who's running, a 10,000 or 100,000 liter reactor and go, hey, grow this for me, they'll be like, what are you talking about? Those knobs don't exist on my equipment, right? I can't do the thing you want. But that's coming. It is inevitable that will happen. Right. Yes.
Yeah, thank you for citing some of the limitations. Okay, well, this was great. Thanks so much for answering our questions.
Yeah,
I really
sure.
enjoyed this.
Thanks to our speaker, Rob. This was terrific. I've learned a ton and really appreciate you being so generous with your time.
Cheers.
Awesome.
Good luck, everyone.
Take care.
Cheers. Bye-bye.